Hello everyone, welcome back to the lecture series, Algorithmic Sustainable Design, the Future of Architectural Theory. Today we're having the fourth lecture. And I will try to cover these topics: cellular automata, the Sierpinski Gasket, and the Seashells. And then I will talk about design in hyperspace in connection to the sacred. So I have a lot to do today, and I will try to relate everything, these disparate sounding phenomena. But after all, I'm digging at the foundations of architectural theory, and we have a lot to do because according to my estimation, there has been a gap for several hundred years. Now, there's a fundamental difference in this lecture, and I want to alert the listeners and viewers of this lecture. Unlike the previous lectures, I'm not going to give practical model for design or practical rules, even though I'm going to look at mathematical models and spend a great deal of time looking at details of these models, the cellular automata. But altogether, I'm putting together ideas from computer science, physics, mathematics, and even spirituality, and I'm trying to make a soup out of these ideas, and I work from analogy. And so all the technical information will be given is meant as an analogy, trying to get into the foundations of architecture, and not as a design rules like I gave earlier, distribution and measuring lengths in order to get a good design. So please keep that in mind. I want to relate the basis of architecture to other disciplines, because in my opinion, architecture during the 20th century isolated itself from the technological world and all of technology's impressive advances. Now, before some listeners get to disagreeing with the statement, I admit that architecture is based on technology, but it is an applied technology. The design concept itself, however, still comes from an artistic basis, whether architects want to admit it or not. Even the most technologically oriented architects don't use science in the way that I, a scientist, or Christopher Alexander, a scientist, use science. So I would, we're really coming back from a different perspective, and that's what I want to do with this lecture and all the lectures. Now, confronted with architecture and the problem of designing buildings and cities, it is one of the most complex problems that the human beings can confront. Now, when scientists face such a highly complex problem, we often create a toy model, which is something out of, say, Legos, something very, very simple that tries to reproduce some of the mechanisms. And then we play with that. Scientists are playing all the time. That's why it's so much fun to be a scientist. You play with a model, and if this model reproduces some of the mechanisms in your complex system that you're studying, then you get an insight into what is happening, and that insight from playing around with the toy model will help you to solve the real problem. Now, this is in contrast with attacking the real problem directly, because often it is so complex as to elude even comprehension, let alone solution. Let me begin now the lecture subject proper with cellular automata. What are cellular automata? They are arrays in which cells can assume different states. We can put different numbers in the arrays, or we can color them in different colors. In this lecture, I'm just going to talk about the simplest type of cellular automata, in which the cells assume binary states, either black on or white off. And we can use the computer notation. On is +1 and off is 0. So these cellular automata change their state in different times, and the times are discrete, 1, 2, 3, 4, 5. And an algorithm that defines the automaton decides how the cells will change in discrete times. So I'm going to further look at the simplest possible automata by going to one-dimensional. 1D means one-dimensional cellular automata. A one-dimensional cellular automaton is a single line of cells. the algorithm will generate the next state. So let me begin immediately by looking at one rule. One rule that I'm going to use during today's talk is turn black if either neighbor is black, turn white if both neighbors are either black or white. A very simple rule. And in order to begin constructing this cellular automaton, I have to specify where we begin. So let me begin with the simplest possible initial condition, where all the states are off except for a single on in the middle somewhere. And here is a picture. We have a single line of cells at time equals 0, and one in the middle is on, and the rest are off. Now, according to the rules I just gave, the two cells, the two off cells on either side turn on, but the cell in the middle, the original cell, turns off. And so on. Applying these rules, I get the time evolution of the cellular automaton, and it goes to t equals 2, t equals 3, t equals 4, t equals 5, and you see that I'm getting nice patterns, pretty patterns. And of course, time can continue infinitely, and I get all these patterns, and this is the cellular automaton. If I had an online computer connection, I could show how this thing evolves, but we don't need that. I'm doing this by hand. As I said, sometimes the simplest explanation is the clearest. Now, this cellular automaton is not presented as a design tool. I'm strictly looking at creating an analogy for understanding architectural design. And I don't mean these patterns to be used directly. This is a problem with talking to architects. They think that when I give a lecture and I show diagrams that these are meant to be copied to build a building. But no, I'm trying to establish an idea, an analogy of thought in order to look at the foundations of architectural design. And the actual sketches for a building are going to look totally different than what I'm showing today. And the reason is that what I talk about does not have the right complexity to be useful in adaptive design. Here is a more concise formulation of the cellular automaton I'm looking at, the one I just sketched, the first few states. If I let the state of the cell at position j on the line and at time t, and I denoted a sub j of t, then the value of a sub j of t can be either 0 or 1. And how do I get that number? Well, I have a recursive algorithm. The cell state at time t plus 1 depends upon the two neighbors. So aj of t plus 1 is the state of my cell in the following step of time, t plus 1. And that depends on the existing states of its neighbors. aj minus 1 is the neighbor on the left, and aj plus 1 is the neighbor on the right. So each one of these numbers can be a 0 or a 1. I add them together, and I take it modulo 2. Everyone knows what modulo 2 means. If you get a 1, it's a 1. If you get a 0, it's a 0. If you get a 2, it becomes a 0. If you get a 3, it becomes a 1. So odd numbers are equal to 1, and even numbers are equal to 0. So that's what we mean by modulo 2. This is just a restatement in a mathematical formula of the rule I gave earlier. And here is even a third formulation of the same cellular automaton. The notation is the pound sign can be either on or off. So if I have a 1 pound 1, it becomes a 0 in the middle. If I have a 0 pound 0, it becomes 0 in the middle. If I have a 0 pound 1, it becomes a 1 in the middle. And if I have a 1 pound 0, it becomes a 1 in the middle. So again, it's another way of writing the same rule. Now, the initial condition is extremely important here because the state of the cellular automata depends upon the previous state. All the cells are on or off. They influence all the later developments. So the initial condition, what you start with at time equals 0, determines all the later development. This example began with just one black pixel on, and the pattern grows to infinite length. there are many different cellular automata, and I have used Rule 90. Rule 90 refers to a classification given by the computer scientist Stephen Wolfram in a new kind of science. That's his big book classifying all of cellular automata. And the one that I'm choosing to talk about today, he labels Rule 90. That's why I keep referring to it as Rule 90. Now, there are many other cellular automata that give different rules. Here is Stephen Wolfram's book. Very interesting if you like if you like algorithms and computer science. I'm not recommending it as a textbook in architecture because there's nothing about architecture in it, but it's a great achievement. Now I want to focus on something on the cellular automaton that I'm using. There are many different types of cellular automata, but Rule 90 is a nearest neighbor rule, namely that everything depends upon the immediate neighbor on the left and the immediate neighbor on the right. And that is the shortest possible interaction distance. It's a very local cellular automaton. We can have different cellular automata, which I can discuss later, that have a long interaction distance. But I'm sticking now to the shortest interaction distance in order to derive a surprising result. And the result is going to be that from the local cellular automaton, I'm going to get long-range behavior. And this is of profound importance to architecture and urbanism, and I will try to tie into that later. Namely, I'm doing something very simple on a very local scale, nearest neighbor interaction, and that will have long-range effects and generate long-range patterns. And that is important for my results. Now, before I go on, I want to come back to what I think are misguided applications. Stephen Wolfram's book has become rather popular in cutting-edge architecture, and Wolfram himself, with whom I am in contact, is being invited to our best architecture schools to give talks. And there's something worrying about this, because from what I read in the literature, some of our architectural theorists are taking his ideas about generating cellular automata and are applying them to create interesting looking forms, and they are then proposing to make buildings in these shapes. Well, I think it's not a correct application, because the Wolfram's cellular automata are just a set of examples. These are mathematical examples that have nothing to do with buildings, because there is no part of the algorithm that is adaptive. So this is not adaptive design, this is abstract design. They're very useful for analogies, and I'm using them exactly for that end in this lecture and throughout the series of lectures, but they're not suitable for design models. Let me continue now to seashells and other interesting things like Sierpinski carpets. The cellular automaton Rule 90 generates a digitized version of the Sierpinski fractal triangle, which we have looked at in previous lectures in the series. Now, remember that the cellular automaton it depends on two things. It depends on the algorithm, and we have Rule 90, so that's the same algorithm we've been using. And we are going to keep the initial conditions that are introduced, namely a single on in the middle and the rest are off. The cells in the line are off. However, different initial conditions will generate distinct fractal triangles. And I will give an example later in this talk. So I just want to say I'm sticking to the initial diagrams that I drew for the Rule 90 cellular automaton. And just to refresh your memory, this is the Sierpinski fractal triangle. Not very complete, because I'm just showing 3 levels of scale. And as we know, the triangles in the corners here, where you get the smaller triangles, there will be further subdivision into even smaller triangles, and then smaller subdivisions of those down to an infinitesimal. So this Sierpinski fractal triangle just shows 3 scales, and not the full fractal. But this is a very popular fractal, so you can find a better picture in any book on fractals. So where am I going with this? I'm trying to lay down the logical framework for adaptive algorithms. And even though I'm not going to talk about actual algorithms today, I will give the basis for the logical framework. When we discover design rules that generate a complex structure like a building or a city, then that building or city will not look like these pretty fractals that I'm looking at, or that Stephen Wolfram has in his book. I'm just using these as analogies. A city or a building looks totally different. What is important, however, is that it has the coherent features of the fractal. So I'm looking at mathematical features that a fractal has, and I'm saying that these features that are easy to see on the mathematical fractal, and here they are, and I'm showing them, and I'm discussing how they arise. These same features also occur in an adaptive building and in an adaptive city, in an adaptive neighborhood, in an adaptive urban space. So that by learning from a very simple but unrealistic mathematical model, a toy model, then I'm ready to discuss the qualities for real-life architectural and urban design. Now I'm going to discuss weaving a carpet. One of Christopher Alexander's favorite things. You know, Christopher Alexander has a phenomenal collection of Oriental carpets, and learned a lot about architecture from them. Well, this is an activity that human beings have carried out all through since the beginnings of history, and we have found woven carpets. The Pazyryk carpet was found in Russia, frozen in the ice, and it dates from classical Greek times. Not made by classical Greeks, made by the nomadic people in Russia. But the weavings have gone on for millennia all over the Middle East, the Islamic world, in Northern Africa. Independent weaving tradition of the American people, indigenous peoples, pre-Columbian, more flat weave than carpet, however, but still, the weaving tradition comes with making cloth. So, this is not a lecture on carpets, it's a lecture on cellular automata. What is the connection? Well, when you weave a carpet, you sit down on the loom and you knot one line of knots from wool. And you knot a pattern, depending on what you have. You knot, say, 2 knots white wool, and then 3 knots blue, and then 2 knots red, etc. And you go horizontally across the line. This is called a warp line. And this is a very complex pattern because you're just looking at a single line that comes into the pattern. And when you weave that line, you go and you weave the second line. And after that, you look at the carpet and it's a beautiful pattern from the top. But each line is rather complex to weave. Now, in order to handle this complexity, in many of these cultures that are nomadic, the complex information that contains the code for weaving each line of the carpet has often been made into a song, so that the master weaver sings the song that tells how many knots of each color, and then followed by how many knots of another color. It is a compactification of information. Otherwise, it's just too much for the human mind to get. And from what we know, all the carpets, or most of the carpets we know, have a regular pattern. So the repetition and the fractal structure, the recursion of the single line then contributes to give the pattern in 2 dimensions. And this is a key point of this lecture. What happens is that we get a space-time diagram both in the carpet and in the cellular automaton. And what do I mean by that? Well, one line is the space where you lay the knots, where you tie the knots horizontally, say, or where you fill in the cellular automaton, which has black or white cells, and then you juxtapose all the different states of the cellular automaton or the carpet next to each other. So one axis is x, the space axis, and the other axis is t, the time axis, which shows the development. And then you plot this on a space-time diagram. Nothing to do with Einsteinian relativity. This is just a representation. The space-time diagram is the two-dimensional carpet, where you see how the thing evolves. And here I have put together the cellular automaton 90 with the initial condition that we have chosen, and you see that it's starting to weave a Sierpinski carpet. You go down as time increases, t equals 1, 0, 1, 2, 3, 4, 5, etc., and you keep going to as long as you want. And I don't know if you can see it, but it's beginning already to create triangles, self-similar triangles. And if we continue, the thing gets bigger and bigger. The triangle gets bigger and bigger, and it will look more and more like the Sierpinski gasket. So this is a really amazing result. We are able to weave the two-dimensional Sierpinski triangle with the rule 90 cellular automaton, which is one-dimensional. Now, there is a difference here in that the carpet is a digitized fractal because there is a minimum pixel size, one cell, whereas the pure mathematical fractal is created very differently. It's created by going in and drawing small and smaller triangles, whereas this is more like a picture on a computer screen. There is a minimum pixel size. However, we get around this just the same way that the audiovisual information gets around that. If we make the Sierpinski carpet large enough, then the pixel size gets very small compared to the overall size, and it vanishes to the limit of human perception. And then if we weave the Sierpinski carpet large enough, it looks like a perfect fractal, even though it's not. This visual example shows emergence, which is important for architecture and urbanism. Namely, what has happened? A recursive one-dimensional algorithm that acts on a single line of cells involving only nearest neighbor interactions has generated a nested design, a two-dimensional fractal on a plane. There is nothing in the cellular automaton to lead us to expect such complex long-range patterns that can be seen only in 2 dimensions. All the scaling distribution, the scaling coherence, the scaling symmetries of the Sierpinski gasket arise from this extremely simple cellular automaton. So it's time for an architectural conclusion, since I have talked a lot without any explicit architectural content. And again, by analogy, I have shown that the simplest possible one-dimensional binary algorithm generates large-scale order. In its generated pattern, which is the 2-dimensional carpet, all the characteristics of the coherence, geometrical coherence, are present, namely scaling hierarchy, scaling symmetry, scaling distribution, some symmetries. And the question is, can we use very simple rules to create great buildings and cities? So I think that I have demonstrated by a single example, by analogy, that the answer is yes. And I can spend the remaining lectures in this series proving that, but I think it's sufficient information for people to think about and to make the connection. The answer is yes, definitely. So what are the very simple algorithms that we can use to generate a large-scale architectural urban order? Well, first of all, we have form languages that I discuss in my book, A Theory of Architecture. Form languages are simple vocabulary of forms that people developed in traditional architectures, a different language for each different tradition. And by using a form language, you get very simple rules, and they create very complex buildings. But each building has a characteristic look. So suppose we go to Upper Egypt and we see the vernacular architecture. It is a product of a form language. that's tied into that particular region, to the culture, to the time, to the available materials. So very simple rules used by the local people, who most of them build their own houses, create extremely adaptive houses, much more adaptive than American suburban houses that waste so much energy and deplete all our oil resources, everything else. You go to another part of the world, in Indonesia, and even in Indonesia, there may be 15 different form languages, depending on the region that you're in. So the form language is an algorithm that contains information, rather simple information, that can be used to create an adaptive building or a city. We use the same form languages on the urban scale, different vocabulary on the urban scale, to create a traditional type of city. And people for millennia have been building the cities using form languages. So that's the answer to my own question. How about today, for those who want to be modern and don't want to use traditional form languages? Well, there is a smart code. And the smart code is introduced by the new urbanists, including my friend Andres Duani and his wife Elizabeth Plata-Zyberg. The smart code embodies a core algorithm that creates adaptive environments, adaptive for human beings. And it's a very simple code, just like a cellular automaton, and I will discuss the smart code in a subsequent lecture. But this is an algorithm that will create adaptive environments. And all over the United States now, municipalities are adopting smart code. Not because they have taken the trouble to look into the theoretical background for this, but no, they have seen other municipalities that have adopted the smart code, and they see that this thing is growing and it has a human scale and people love to live there, and the real estate prices go up. Whereas municipalities that keep the old suburban sprawl zoning codes are just as dreary as any awful suburbia with strip malls today. So this is to be observed, that the smart code creates adaptive environments. Now the adaptation, you may or may not object to my use of the word adaptive. How can a single code create adaptive environments? And the answer is that the smart code contains a core which is universal. It can be applied anywhere in the world with some calibration. The calibration makes it adaptive to the local requirements, and then the pieces that add onto the code are specifically location and culture dependent. So those parts of the smart code make it adaptive. But this is not the time to talk about the smart code. That comes later. So let me get back to the concept of emergence, because this is so important in architecture and urbanism. The simple rule creates a complex pattern that is not explicit in the initial code, yet it must be there somehow. It's in the DNA. But if you look at the DNA, you certainly don't read. If you look at the DNA of an elephant, you certainly don't read large animal with big floppy ears and giant tusks. You cannot read that, but it's there. It's all coded there. So from our point of view, the self-similarity and the scale coherence must be there somehow, but it's certainly not obvious. The emergent geometrical patterns are seen only in the higher dimension than the one the algorithm acts on. What algorithm have we used to get all my results today? A one-dimensional algorithm, a one-dimensional row of cells. And what have I gotten? I've gotten beautiful triangular patterns on 2 dimensions. So you cannot see the original, you cannot see the symmetries in the original dimensionality. That's important for discussing later. Now, is there an animal that has applied a cellular automaton to build its house directly? Yes, it is. Several seashells, marine mollusks, have used the Fractal algorithm to build their shell. The 10th olive shell, the Damon's volute, the textile cone, and the glory of the sea. How does the animal do that? Well, the animal lives in a small shell and then grows the shell by laying down a calcium carbonate on the lip of the shell, so the shell grows in a helical fashion. And apparently, these shells, the animals living in the shell have the knowledge to use a one-dimensional cellular automaton in order to create a Sierpinski-like pattern. So these animals are much cleverer than we give them credit for. And here is one seashell that has not very well, the pattern is not very well drawn, but maybe, these are clever animals, but not as clever as the octopus, say, which is much cleverer. So, but there's something going on here, and you can see that it looks Sierpinski-like, and some are more Sierpinski-like than others. But it's obviously a cellular automaton. There's absolutely no doubt about that. So what is amazing here is that the mollusk is using an algorithm, a one-dimensional cellular automaton, to build its house. Now, the mollusk never gets to see the outside of its shell, like we go outside to see our houses and inspect if they look pretty or not, because it always lives inside the shell. The eyes are not as highly developed, and even more amazing is that many of these shells, while they're alive, the shell is covered with a membrane, organic membrane, so the pattern is not all that clear to see. Well, the shells we buy at the shelf shop are dead and they have been cleared. The membrane has been cleared off, so we see the pattern very nicely. Anyway, these are unanswerable questions. I'm going to take a little detour to relate the one-dimensional cellular automaton, again Rule 90, to the binomial theorem. The binomial theorem is one of the great achievements of mathematics in history. It was developed by Sir Isaac Newton in Cambridge, England. Now, binomial coefficients are the numbers that come out when you expand a plus b to the nth power. And all these numbers, which are the binomial coefficients, they can be computed from Pascal's triangle. Blaise Pascal is a French mathematician that lived after Newton. And by some mathematical steps that you don't need to follow. Here, if I were giving a lecture series to mathematical class, I will go through all these steps. But it's just of general interest that somehow from the binomial theorem you get the Sierpinski triangle again. And back to the seashells. So how does this work? Here is a binomial expansion. A plus b quantity squared is a squared plus 2ab plus b squared. And those coefficients are what's important. The coefficients are 1, it's the coefficient of a squared. 2 is the coefficient of 2ab. And 1 is, again, coefficient of b squared. So those numbers are 1, 2, 1. For the cube, the coefficients are 1, 3, 3, and 1. And for the fourth power, the coefficients are 1, 4, 6, 4, 1. So I don't care about the a's and b's, I just care about the coefficients. So here I'm going to write down the coefficients, and I get what's known as Pascal's triangle. So you see 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Again, making a diversion from a diversion, this has a very beautiful structure because every entry in Pascal's triangle is the sum of the top two entries. For example, look at the 4, and above the 4 you have a 1 and a 3. 1 plus 3 is 4. Look at the 10. Above the 10 we have a 4 and a 6. 4 plus 6 is 10. So things are adding up to generate the lower rows of the Pascal triangle, and we can continue indefinitely. So we have gone away now from expanding powers of a plus b to just adding up numbers. And here is the algorithm for generating the rows of Pascal's triangle. Just add the two numbers that already exist in the triangle to get the number directly beneath them, and you continue to generate more rows. The result, this is the result I want. I take the Pascal's triangle that I have written for you with all those numbers, and I take it and I rewrite it modulo 2. You remember what modulo 2 says? All even numbers become 0, and all odd numbers become 1. So this is Pascal's triangle modulo 2, and lo and behold, we have the Sierpinski triangle. So we have obtained the Sierpinski now from the binomial theorem rather than from a cellular automaton. What does this all mean? Well, this links things together in a way that makes possible new ideas and new theories. The classification of cellular automata. Stephen Wolfram has classified all 256 possible one-dimensional cellular automata with binary states, namely on and off, or 0 and 1, and nearest neighbor interactions. 20 of them, of the 256, generate variants of the Sierpinski gasket, whereas others are not regular. So that's 8% of all possible cellular automata. Now, we don't really care about cellular automata with binary states and nearest neighbor interactions, but I'm getting a figure. I'm getting a figure about the selection of algorithms. The useful algorithms are going to be very few. In this example, I get 8% of all possible algorithms that have anything to do with the problem at hand. And the problem at hand is not even building a house. The problem at hand is creating a beautiful triangle with internal symmetries. So out of an enormous number of possible generative codes, very few of them can be possible architectural algorithms. So having established the possibility, or not even the possibility, having established the existence of algorithms for design of buildings and cities, and having mentioned to you that a traditional building and architecture uses such algorithms, now we ask, how do you decide if a particular algorithm is useful or not? And this is the topic of following lectures. However, even at this stage, we can say most algorithms that you can find lying around or dream up are not going to be adaptive. A very, very small number of all possible algorithms can be used for adaptive design. This is what the previous slide demonstrates. To select algorithms, therefore, we are going to need some criteria, and those criteria are going to be developed in following lectures. To use the examples that I have at hand, the Rule 90. Why is Rule 90 useful? Well, for two reasons. I see it in biological structures, I see it in the seashells, so there must be something to Rule 90 that's important. And also, it's related to the binomial theorem. And most people listening to me will not know that Rule 90 was related to the binomial theorem. So these unexpected relations and applications to natural structures, biological structures, single out Rule 90 as something special. And that's why it gives the beautiful patterns. Now, again, I'm not going to use Rule 90 to build anything. It is just that I'm motivating why I singled it out. Before I'm finished with Rule 90, I'm going to go back to what I promised you, in that Rule 90 does not only generate the Sierpinski triangle, it generates beautiful nested hierarchical patterns that don't look like the Sierpinski triangle. And the way to do that is to begin with a different initial condition. As I said earlier, the entire pattern depends on the initial condition. So let me begin with a different initial condition, namely 11001, and see how that develops. This is how it develops. So you see at the top line is black, black, white, white, black. That's 11001. And Rule 90, which I gave you in the beginning, evolves this triangle. And if you squint and look carefully, you see that it is repeating. There's a nested quality. There's a repetition. And the repetition continues. You can continue to grow this cellular automaton and get more and more rows and get a beautiful nested pattern, which is totally different from from the Sierpinski Gasket that grew from the other initial condition. Now, how many different initial conditions can you have? You can have an infinite number of different initial conditions for this rule 90. And here we have another important result. Can I say result? Not a scientific result, but a result by analogy for design. Adaptive design is highly dependent upon initial conditions, namely the existing structures, the surroundings, the human needs, the culture, etc. The same design algorithm will result in drastically distinct end products. Therefore, the proper algorithm can be used to design buildings and cities that are each distinct because they adapt to local conditions. In my estimation, this is one of the most important results I have presented so far applicable to architecture and urbanism. Not a mathematical proof, but I think it's fairly convincing by the little mathematical toys I have used. But think of it. Even a single form language applied to different sites, different initial conditions, different environments, will generate totally innovative structures that are adaptive, if that algorithm is fine-tuned to generate adaptive buildings and cities. So this, with one stroke, we can say, this does away with the terror of restricting architectural creativity. So many contemporary architects argue, well, if we start using traditional form languages, we don't have any creativity left. That's mathematically wrong, because we can, I have just shown you that you can generate an infinite number of different buildings. My friends, the classical architects, know that. They know that they have a classical form language that is adaptive because it has worked for many thousands of years. They can go and use a set of initial conditions on a site and generate a beautifully adaptive building that's not a copy of the Parthenon or any classical building. But it is classical, yes, it looks classical, it feels good, but it's totally innovative. A new building using the same form language but using different initial conditions. By contrast, formal design is not adaptive. And formal design can be of either two forms. One, it could be non-algorithmic. It doesn't compute anything. It just has a form, a standard form, and it imposes the preconceived form onto the site, imposes something as a solution that's not really computed solution. It is preconceived. It cannot possibly be adaptive. Unfortunately, we see so much of that all around the world today. The second case of formal design that's non-adaptive is more difficult to argue against, but is just as non-adaptive, because it could be algorithmic. Somebody could be computing something, and you say, well, it's computing something, so it must be adaptive. Absolutely not. It is algorithmic, but it's computing something not responding to initial conditions. It is computing something according to internal criteria which are self-referential. So you can have these two types of non-adaptive structures, and we see them all over the world today. We have just a cube imposed all over the world that can serve for a schoolhouse or a bank or a private residence or a government building or anything. Just the same silly cube that adapts to none of those situations. Or we have these architects who say, well, I'm going to do an algorithmic design. And here I'm doing an algorithmic design. I'm computing this, and the form is evolving. And look at this fantastically beautiful, complex form. Well, that may or may not be adaptive, because depending on the criteria. And many of these architects I happen to know for a fact, because I read their papers and I look at and analyze their forms. They're computing according to self-referential criteria. They're not computing based on adaptivity. Therefore, the result may look complex, but it's no better than the glass box or the concrete cube. It does not take into account human needs. So again, I come back to the question, how do we choose algorithms? Well, let's look at nature. Nature uses only sustainable algorithms. Sustainable in the correct sense. Because non-sustainable algorithms die out. So the algorithms that we observe in nature must be sustainable. Otherwise, we did not observe them. This is Darwinian selection based on the survival. It's a survival of algorithms that are selected on the basis of sustainability. So it's a selection of algorithms. This is very different from the selection of forms that we normally think of as the result of evolution. When we say, well, the crab has a shell, it's of a specific form because it has been selected as an optimal shape for this marine animal to be in. Yes, that is true. It's a selection of the form of the crab shell over millions and millions of years that has evolved. However, that's not what I'm talking about. I'm talking about selection of algorithms that processes that do something, that design something. It's more like the processes of how the embryo grows, of how our DNA influences the growing embryo. The selection of processes is more difficult to visualize than the selection of a form. But unfortunately, we have to start to think about the evolution of algorithms, because if you take my series of talks seriously, the future of architecture depends upon grasping what an algorithm means and then applying it to architectural and urban design. And now that brings me to something that may seem totally unconnected, but in fact it is highly relevant. Design in hyperspace and connection to the sacred. This is totally speculative. However, I think that you will recognize that this topic is fundamentally important to architecture. For millennia, human beings have sought to connect to the sacred realm through architecture. Christopher Alexander talks about connecting to a larger coherence, something there. It is a visceral feeling. This is not intellectual. This is visceral. We feel it right inside our heart, inside our belly. We experience this connection in a great religious building or a place of great natural beauty. And it doesn't have to be a great cathedral or one of the greatest mosques in the world. Hassan Fatih, the great Egyptian architect, talked about the sacred structure in everyday environments. Occasionally, very rarely, we sit somewhere in a very ordinary environment and we feel totally connected, totally at peace with that. We experience this connection. It is, if you have experienced it, please go back in your memory, and I'm sure you will see that it is very rare in a post-industrial or industrial environment. Usually we experience it either in a natural setting or in a traditional built environment, and there's an important reason for that. Islamic architecture has always tried to be connective. Here are just two sketches from Cairo, 15th century Cairo. The connective elements are what today's architects dismiss as useless ornamentation, but these are the connective elements. These are what lead you to the higher connection. And it just shows the total wrong-headedness of the way that we misunderstand architecture today by dismissing the most important parts as irrelevant. Now, even talking about it, and some of my listeners today, you may feel that you may feel uneasy me talking about this, because today's Western culture does not accept a connection, a profound connection to places and buildings that connects us to something beyond reality. The Western culture does not accept this as possible. Strangely enough, because we don't understand it scientifically. Well, this lecture is designed to give some ideas of how we can understand this scientifically, and hopefully we'll clear up this misunderstanding once and for all. Let me do some mathematical background. Excursions to higher dimensions. Let me review the different dimensions. A line exists in one dimension. Okay? A plane exists in two dimensions, x and y. A volume exists in three dimensions, x, y, and z. In mathematics, which I do every day, it's perfectly normal to work in any number of dimensions. We say, consider a n-dimensional vector space, and we do operations, and we solve problems, and we write papers on n-dimensional vector spaces. However, most people are not mathematicians, so that does not really connect to the heart of normal people. But so instead, I'm going to rely on physics. From physics, we know that ordinary matter exists in several dimensions. What do I mean by that? The matter itself is composed of atoms, and atoms are composed of elementary particles. Those elementary particles exist on different dimensions than x, y, and z. There are internal dimensions that lead to internal symmetries. So this is not religious speculation. This is not mathematical abstraction. This is the matter. This is this stuff here. What everything is made out of exists in other number of dimensions. And just to mention it, we have the three special dimensions, x, y, and z, and the next dimensions distinguish the particles. For example, the spin is a dimension that distinguishes bosons from fermions, different types of particles that combine together to make atoms, and atoms make the matter of which we ourselves are made of, and everything else in the world is made of. The isospin is another dimension, different from spin, that distinguishes nucleons, the proton from the neutron, and creates the nucleus that is in turn linked to the electron to make the atom. Going further in, the hypercharge is another dimension that distinguishes shorter-lived elementary particles. When we create short-lived elementary particles in an accelerator, they live fractions of a millisecond, but they're distinguished by another dimension, which is the hypercharge. So here, this is no longer mathematics. This is physics. How do I apply these concepts to architecture? Well, I imagine, now this is speculation, imagine an architecture in hyperspace, a complex design or structure defined in more than 3 dimensions. Let me assume that the structure is richly patterned, that has symmetries, that has a scaling, that has all the elements that I've been talking about for actual 3-dimensional architecture. But if indeed we have an n-dimensional structure that shares all these symmetries, then we cannot perceive the totality because we can only see things in 3 dimensions. So we see sections of the whole n-dimensional structure. And what is a section? Well, you take an orange and you cut a slice through the orange. That's a section. It's a 2-dimensional section of a 3-dimensional structure. And here's the central conjecture I want to make in today's talk. We connect to a higher realm only through coherent complex structures, if we connect at all. But if we do, then coherence and symmetries of form make possible the continuation into symmetries in other dimensions. Now, most of 20th century and contemporary buildings restrict forms to 3 dimensions or less, because they are minimalist or disordered. Being minimalist or disordered structures means that they don't have the symmetries, they don't have the coherence, they don't have the scaling hierarchy, they don't have the scaling symmetry, the scaling distribution. So according to my conjecture, there's no way they can connect to anything in higher dimensions. Now, this is where I connect with the previous part of the talk. I used a 1-dimensional cellular automaton to construct a 2-dimensional Sierpinski gasket, and I spent half an hour doing that. I want to use this now as an analogy. We, human beings, build 3-dimensional material structures that could generate a larger coherent structure within n-dimensional hyperspace. And then we could thus connect to the larger n-dimensional entity, which is more than we can see, because all we can see is something in 3 dimensions. Just with the Sierpinski gasket, which is 2-dimensional, it is not possible to deduce its large-scale nested symmetries and patterns from any single section. But we do observe regularity in each cellular automaton with Rule 90 that generated the Sierpinski gasket. So this is an important point. The geometrical coherence in what we see implies a larger coherence in n dimensions. And here I'm intentionally confusing two things. One dimension going to two dimensions in the Sierpinski Gasket, using that as a toy model, and the most important, more profound conjecture that we live in three dimensions, and by creating ordered symmetric structures in three dimensions, we connect to a structure in many more dimensions. And this is the piece we see. We create it and we connect to a larger state of being in larger dimensions, which sounds totally crazy, but I'm just laying out the groundwork for this. Now, I'm using our toy model. Here is the Sierpinski Gasket, and I will take a line through. This is one section of the Sierpinski Gasket. Let me go back to show that. So the cellular automaton that's on this line of the Sierpinski Gasket shows some lines, just shows some dots here, and the rest is white, because you see where it goes through the vertical, the down-pointing triangles, those are white, there's a gap, so all you see are just some little vertical lines. Can you, looking at the single one-dimensional line, deduce that the Sierpinski Gasket has this beautiful nested structure? The answer is no, but that single line, the cellular automaton, does have regularity and symmetry. So the self-similarity and scaling on the complex two-dimensional object, which was our triangle, it shows as a reduced coherent patterns, but still there are coherent patterns with similarity and scaling on the one-dimensional cellular automaton. Now, continuing in this conjectural direction, how can we connect to coherent structures in n dimensions, since we lived in 3 dimensions? Well, it just so happens that the answer exists in mathematics, because mathematicians are used to eating n dimensions, where n is any number. They eat it like breakfast cereal without any problems. If we inhabit a space that is bounded, like we are bounded in 3 dimensions, then we think that we cannot connect to something outside it. However, by going to one more dimension, we can jump over the boundary and connect. Let's think what this means. And I will show a nice diagram that I obtained from the great Russian mathematician Israel Moiseyevich Gelfand, showing how it's possible to jump in 3-dimensional space to get over the 2-dimensional boundary. So suppose we live in a 2-dimensional space that is bounded. We cannot get out of our 2-dimensional space to connect to something outside. What we do is put our 2-dimensional space into a 3-dimensional space, and then we make a little jump. You see, you have to jump up. So you need a 3rd dimension. You can jump up, and then you go outside and make the connection to the outside. So for whatever it's worth, this diagram hopefully will raise some ideas and raise some questions. I have raised questions without answering them. The best kind of questions to raise. About connecting to a higher state of order. How do we make this jump out of physical 3-dimensional space of buildings so as to connect to a realm beyond 3 dimensions? Well, the religions tell us that this is possible. I'm not qualified to discuss the religious aspects, but there are many people who claim that this is possible. So let's see. There are also mathematical and physical questions about these extra dimensions more than 3. Are the additional dimensions of our existence interior or exterior? I think it's a very good question, and I have not heard anyone raise this before. The spiritual approach imagines a world outside our everyday realm. So just the English words tells you that there's something outside 3 dimensions. However, the physicists who have discovered the dimensions, the extra dimensions, have discovered dimensions inside, the internal symmetry of the elementary particles. The conjectural picture presented here highlights questions about connecting to a higher order, whether the dimensions are inside or outside. It's a question that philosophers can debate for many years. Christopher Alexander addresses this topic using empirical evidence presented in the Nature of Order Book 4, The Luminous Ground, which I recommend that everyone read. Have we reached the limits of biology? How high can we rise in our emotional connection and still explain it biologically? We do get emotional high from love, music, art, architecture, poetry, literature. The mechanisms of response are all due to our sensory apparatus. They're biological, although the most important elements are still incompletely understood. It is human beings are capable of an emotional response that goes far beyond our purely animal qualities, just of finding a mate or finding food or avoiding a predator. I'm interested in the conditions for sacred connection, but I'm not interested in the mystical properties. I'm a scientist, and I'm interested in the geometrical qualities, trying to understand these connections. So let me look at existing ways of connecting. There are existing ways of connecting through dance, music, art, and architecture. And each one of these endeavors features patterns, regularity, repetition, nesting, hierarchy, fractal structure, scaling, all that I have been discussing in the series of lectures so far. The highest artistic expression is often related to religion. In the West, we are proud to have Bach, Mozart, Botticelli, Michelangelo. The Islamic world is a highly connective world, and there are so many anonymous artists and architects of the Islamic art and architecture. By seeking God, human beings attain the highest level of connection to the universe. Any religious person will tell you that. Spirituality can lead to connectivity, and it has nothing to do with any particular organized religion. Is this the same mechanism as biophilia? Something I mentioned before. Biophilia is the intrinsic connection we have with other living beings through our common genes, and we relate to them. Is it the same connection? I don't know. Maybe it is. Or it could be a more advanced and more intense connection that we need and we thrive upon, and it nourishes our body, as many religious people will tell you. This is this emotional and physical nourishment. So how can we transcend biological connection to achieve an even higher spiritual connection? I cannot answer that, but again, I'm going to look for mathematical qualities. I cannot explain religious belief because it's an abstract concept resident in the mind. But the methods of connecting to the higher realm are through geometry, music, rhythm, color, and our senses. And the connection is very physical. It's intensely physical for those who achieve it. It's the mystical experience. Dance. All cultures have mystic dances that have religious purpose. Bharatanatyam, the classical Indian dancing. For centuries, people connect to the Hindu gods through the dance. African shamanic dancing, Native American religious dance, the whirling dervishes in Mevlana, Turkey, Hasidic dancing. All these are mystical dancing, the mystical dance forms. If you analyze them coldly as a mathematician, you find the geometrical qualities of scaling, repetition, scaling coherence. In music, sitting down and listening to music or playing music, we have the religious music of the West, the masses of Bach, Haydn, and Mozart. They have been studied intensely by mathematicians. You can read many articles on the music of Bach and Mozart showing the fractal temporal structure. Exactly what I'm talking about, only it occurs in the temporal dimension in the music. The Sacred Chant in all religions connects the individual to something there through the chant, through singing. For example, the Passion plays, the St. Matthew Passion of Bach, the Byzantine Easter service, the Kol Nidre during Yom Kippur, Buddhist ceremonial chant. All of these connect the individual, and again, calming down the body that gets excited when it connects in this way. It's an overwhelming experience if you've had it, and I hope most people have had it. analyzing from the cold eye of the mathematician, you find the same nested patterns that I'm talking about, and in the scaling hierarchy, in the structure of the music itself. So there is something there mathematical. And finally, we come to architecture, sacred architecture. All over the world, regardless of the culture or regardless of the specific religion, the house of God displays the qualities that we seek to the highest possible extent. Namely, I seek and my friends seek these mathematical qualities of scaling and hierarchy and recursion, independent of particular religion or style. And it is found among all religious building types, whether a temple in Japan, a great mosque in Iran, a cathedral in Europe, a church in Mexico. All of these share the same type. So architects of the past instinctively build according to rules for scaling coherence. This is something that is observed. To conclude, all the examples I have mentioned have common mathematical qualities: fractal symmetries, rhythm, hierarchy, scaling distribution, etc. They are deliberate creations by humanity the world over, trying to connect to something out there, or is it inside there? I have raised questions without answering them, and I'm glad to have done that. I would like this series of lectures to stimulate thought and investigations, to make connections that perhaps people had not made before. I take this from my friend Christopher Alexander. Just talking to him for half an hour, you make 50 different connections, and then you're left with the next year pursuing these connections. I like to do that. So in this lecture, I've not presented any data. You do this in order to create a nice window. No, that's in other lectures in the series. But I have presented complex ideas and links by analogy, and I may be criticized that these links are far out and not clearly established, but many of them I believe I'm making for the first time. So even if these things are not well defined, I hope they will give rise to some investigation and food for thought, and we desperately need that in order to create an architecture for the 21st century. So this is all for today. Thank you very much.